So Doruk, you have a question? Your hand is raised.
Hocam ilk ödev list üzerinden mi olacak diye sormuştum ama.
Yes. Hala ödev çıkmadı değil mi? Okay. I think the homework should have been out by now, but I'll check with the TA. It may be delayed, but it will be on Lisp. So general programming in Lisp. So you'll be doing some Lisp programming, learning and programming in Lisp, common Lisp. All right. So there was a question also regarding the PS sessions. And my answer to that is, I don't know. So we were planning to do a PS session, but last week somehow the TA didn't do it. He apparently posted something on Moodle, but Moodle was down for some other reason. So you might have noticed that actually we renewed the Moodle stuff and we put some new, or at least some of the stuff back on the page, Moodle page. So if you haven't checked from last time, you can do so. There are the slides, and also I placed some assignments for reading. So I think I put first 2 chapters as a reading assignment. So quickly read them and be aware of those, what he says in the book. All right, I think we have 2 more minutes. I'll start exactly at 2 o'clock. If there are any other questions, please let me know. And also make sure that your microphones are muted when you are not talking. There is a background noise that I can hear now actually, and it seems that someone's mic is on. So please keep them muted. And this session will be is being recorded right now. And you might have noticed that we already put the last week's first lecture on YouTube. So, and another notice went out last week also regarding the copying of the lectures. So you are not supposed to copy or download or record or whatever any of these lectures. As I said, I'll be making them available on YouTube. And other than that, any copying will be a violation of copyright laws or whatever. So if there are no other questions, and we are almost there at 2 o'clock. Yeah, it is 2 o'clock. So let's continue from where we last left. Last time we have gone through all these programming languages. Someone's mic is on, please mute it. I'm hearing someone whistling. Hello? Please mute your phone, microphones. Hello? Okay, I'm not gonna start talking till someone actually does that. So let me see if I can see it here. I can probably go here and mute everybody, right? So where is this? No. Mute them all. All right, so I guess it is done now. All right, so the question then is, why do we have this course, right? Other than we need to pull some credits, put some credits, but it must be something in this course that is gonna be useful for us, right? So again, if you recall the definition from Perlis, he was saying that a language is a conceptual universe, but should have several things in it. First one is it should provide a kind of a framework for solving problems, and it should actually provide useful concepts and programming methods. So this is fine. This is what kind of a language, a programming language should be doing. So then the purpose of this course should be around this, starting with an understanding, developing an understanding of the language you might be using today, and doing this so by comparison. So if you are using C++ or Python or C or whatever it is, do you actually the capabilities of this language from the framework perspective? Does it actually, do you know what type of framework it provides for solving problems? So it is, if you are choosing it, must be having something useful. It must have some useful concepts and programming methodologies in it, right? So we want to understand actually, or we want to give you an understanding of the kind of the language that you are using, and not necessarily just with respect to these concepts and frameworks and so forth, but also by comparing. So we'll do from time to time quite a bit of comparison between various languages. And of course, knowing the history of actually these programming languages gives you a perspective, and we want to hopefully appreciate this history of diverse ideas, diversity of ideas in the programming community. And also very important is we want to be actually prepared, or want you to be prepared, a new programming method or a paradigm or tools when you need them or when it comes. So it may be that during your, let's say, studies here, it may be C, C++, and Java might be sufficient to do a lot of things. But when you go to the real world, sometimes the problems that you are going to be encountering may require, let's say, more useful concepts or some other useful concepts or programming methodologies or some other framework that is more suitable to solving the particular problem that you are actually solving, right? So we have quite a few of these things out there. And if you know the concepts, for example, if I know what functional programming means, it will be quite easy for me to actually learn a new functional programming language. It should be relatively easy. So if I know a little bit about syntax and semantics, how it works, how the syntax is actually designed, and how semantic works, you are going to actually easily learn, or this in the first iteration of learning is going to be quite easy, because you know the concepts already, and if there are some variations that this new language actually is bringing, then you'll be just picking up on those, not necessarily repeating everything else. So this course should prepare you for new programming methods, to learn, easily learn new programming methods and paradigms and tools. Okay. Are there any questions? Someone is, I think, let me see if I can find this person. Someone's microphone is on and I cannot mute it. No. How come? Seems that everything is muted, but I still hear you. All right. Okay. Let's see. And as we, I mean, in engineering, you need. We are trying to actually get you, or we're trying to have you build some, let's say, critical, have some critical thought, thinking on identifying properties of languages. It's not just the syntax or the sales pitch. We are going to see an example of it in a few minutes, but real properties of the language. Why does it matter? Why does it matter? Why does it actually differ from another one? When we talk about C++ and Java, you learn the main differences between them. Now we are gonna look at these in a little bit of a different, let's say, in a formal way. Try to identify, or will be able to identify, properties of a language. Okay, and we are gonna learn that actually in this is every convenience has its cost. So nothing comes free. So there will be always a kind of a cost related to something that you would actually choose or in your design, right? And we need to recognize the cost of presenting an abstract view of a machine. So this means that, again, kind of programming is, or programming languages actually try to provide and present an abstract view of the machine. And there are costs related to this one, and we need to actually understand those costs. We need it because if that abstraction is not there, it will be impossible for many of us to learn actually proper programming, or we are not going to be able to actually properly program those machines to actually do useful stuff. But that abstraction actually has costs in them. Sometimes we are going to see that it is cost in terms of, let's say, safety. Sometimes the cost is going to be in terms of quite a bit in terms of actually the effectiveness of the code that will be actually generated by your language. So we need to actually recognize these, or we'll learn how to recognize those. And also we need to develop an understanding of the trade-offs in programming language design. So there will be, again, if nothing comes for free, so that means that we need to actually choose some of these costs over the others. And that question of actually which one is and what type of trade-offs there are in that selection, in that design, we need to understand that. And this course will help you to actually develop that understanding. And this is a kind of an older slide that I keep here and I update from time to time. We need to also understand, I mean, from the, we did this last, the first class, the first lecture, to understand the trends and why they are actually happening. So we saw that, okay, top 3 was kind of shared between Python and C, C++, and Java, right? So top 4, let's say. And why is this so? So sometimes you see that actually type safety is going to be an issue. You don't know what type safety is properly right now. We are going to talk about what a type safe language is. But you see that, let's say, in late 2010s, or for the last 10, 15 years, type safety is kind of has become an important topic in programming. And then scripting languages and other languages for web applications have been quite popular, right? We have seen those. Now, these are again driven from the need, and recently we see the mentions of actual functional programming coming up again and again because of its let's say use in concurrency, and also the same thing, some mathematical let's say framework for some languages may help us actually in developing, or at least developing, let's say these blockchain type of applications, or blockchain applications can be developed in or addressed in using some languages better than some other languages. Again, some languages have these properties of safety built into it and scalability built into it. And because of those, it might be easier to use those languages. In the teaching trends, commercial trends, we have seen the commercial trends more or less. On the teaching side, meaning what do we teach as a first language in computer science and computer engineering, let's say, disciplines. C was there from the beginning, and Java replaced it quickly in the, let's say, mid-90s. And in the last 10 years or so, we see that actually Python has done what Java has done to C, right? So Python seems to be kind of a go-to language for teaching in engineering, computer engineering, and computer science disciplines. Why? Because again, we are going to see some of these, or at least we are going to be able to say some of these whys later on during the course of the year, the semester. Python is easier to read language, so it's a language that is actually designed to be very easy to read and relatively easy to write. So Python, for example, doesn't have, let's say, curly braces or punctuations, or let's say some, let's say, syntax that we used to see in C and like Java-like languages. And that actually makes that thing readable, more readable to a newcomer to the area. And you don't see curly braces in your regular life. Probably, if you besides math and some scientific, let's say, publications, you don't see curly braces, right? But C is all about curly braces. I mean, C, when you look at it, you see curly braces. The first thing that kind of pops up is curly braces. So that means that actually you have something, an artificial construct there that is not, let's say, readily understandable or readily readable by a newbie to this area. Python is kind of, let's say, going away from that and making it more readable and so forth. Of course, it's not going to be as if it's a, let's say, natural language, but it can get closer to that than some others. And from the perspective of teaching trends, we had sometimes this Objective-C because of all these hype about iOS and iOS programming, app programming, and so forth. And you have seen that's if you look at, let's say, Google Trend or other indices that I have shown you the other time, Objective-C and later Swift came, and it has some let's say, followers from a teaching perspective as well, but it has been diminished lately. So these are also, again, the teaching trends and the commercial trends. They are not actually happening in a vacuum, right? So it has been shaped by the real need outside. So when you need a lot of app programmers, when you make a lot of money programming apps, then you have Objective-C or Swift or whatever for iOS and maybe for Java for Android devices. Okay. All right. And so, and then when it is, let's say, especially these days, when everybody is trying to do some sort of artificial intelligence, machine learning, deep learning, and so forth, or data science, then Python kind of emerges as a replacement for Java, which was a replacement for C. It emerged because of portability and also safety reasons that C was not able to actually address, as well as Java has done, and later on as well as Python has done to Java. Because again, when you talk about data scientists, for example, you have now a new breed of, let's say, an occupation where people need to do a little bit of a programming, not much. They are not going to develop algorithms. They are going to use algorithms. They cannot do it visually using, let's say, just a table and so forth, like Excel or whatever. So they need to do some programming, but the level of programming is not supposed to be as deep as, let's say, what you would do when you do, let's say, a complex algorithm, and when you require quite a bit of efficiency, effectiveness, efficiency in terms of runtime, then you don't need C, and you need something. You still need something. If you use Java or C for that purpose, it turns out to be an overkill, because these are not people that actually are, let's say, educated in the sciences and engineering of our discipline. They might be coming from math, they might be coming from, let's say, physics, they might be coming from mechanical engineering or whatever, and those people need to still do some programming using a lot of libraries, and then it turns out that Python was a good, actually, thing for them, and Java was not such a good thing, because Java still required some reasonable understanding of, let's say, object-oriented programming, which, if you are not taught in a class what an object-oriented programming is, you would not easily understand it. So Python, you can program Python just as an imperative language, as well as a maybe a little bit on object-oriented programming, using object-oriented programming paradigms, or even, let's say, functional paradigms. So you can actually add on top of it as you go along. So Python is a very, very involved language, but you can still start to use it at a very low, very, let's say, rudimentary level, and achieve something with it. Okay. And then again, from the research and development trends, modularity is still an important thing. Standardization of new module features have been added to Java and C++. Another thing that actually is quite important is program analysis. So can we do automated program detection? Do we need new programming environments, and how do we do the compilation? These type of things are important, and there have been there is quite a bit of research in this area. Another one is actually isolation and security. So things like sandboxing, language-based security, and so forth is an kind of an active research area and development, research and development area. This is a little bit of, again, old slide. We have here in, Web 2.0 for increasing client-side functionality, mashup isolation problems, and so forth. Now I can add to this one also things like, let's say, languages that may better address, like, let's say, distributed concurrent programming with safety in mind, safety and security in mind. So like, let's say, blockchain. So it turns out that actually there is quite a bit of language research going on the blockchain side. I'll touch upon that when we talk about functional programming later on. So let's look at an example. This is not a specifically chosen example because it's an important language. We haven't seen this in our list of languages, popular languages, but there is a language called D. And when you look at actually its sales pitch, this is the language's sales pitch, it says it's a culmination of decades of experience implementing compilers for many diverse languages and has a unique set of features. Now, when you hear something like this, you say, okay, you know, these people that developed D or designed D has quite a bit of experience in implementing compilers. Not just that, but not compilers not for a single language or single, let's say, framework, but many languages, many diverse languages. And when you combine these things, you'll have quite a bit of a complex thing probably. So we said, okay, if I have experience in compiler design or implementing compilers for many diverse languages, then I need to also have some good insights into this cost analysis that we discussed, right? So nothing comes free. So if I actually know many diverse language properties and put them together into one, then I may be making something very nice, very powerful, but I am sure to actually bring in some problems, some costs because of those choices that I make. So they don't say it, of course, here. This is the sales pitch. This is their first page. And they say they have high-level constructs for great modeling power. We don't know what this means. First of all, what is a high-level construct? And what do you mean by modeling power? What is modeling? What is modeling power? We are going to talk about this later on. They say high performance compiled language. So this is kind of a giveaway that they have something in mind in terms of, they have some constraints in mind in terms of performance. So they seek high performance, and usually high performance is actually attained using a compiled language. You don't know yet what a compiled language is and what a interpreted language is the alternative, or maybe some hybrid, right? But they are going for compiled language because of the desire to achieve a high performance, let's say, program at the end. They talk about static typing. This is a very important thing. We are going to discuss this. There are alternatives. Alternative is dynamic typing. And there are differences. There are advantages and disadvantages of both. And they don't address everything perfectly. So we'll see what it means later on to be doing the typing using a static typing or or dynamic typing. Typing here is not typewriting. It's typing here means that I have data. I need to manage data with my language. Within my language, I will manage data, and data should have certain, let's say, types, and we manage data by assigning types to them. And there are different ways of actually maintaining and let's say checking and doing and whatever that we do with these values or with this data using static typing or dynamic typing. So it says, for example, it has a direct interface to the operating system's API and hardware. This is interesting. So they say that, okay, I have direct interface to the operating system. We haven't discussed this quite a bit in many languages that you have seen so far. So we sometimes have, most languages will have some sort of an interface to the operating system. But having something direct is kind of maybe interesting, and it may be advantageous to have such a thing, but it may be also disadvantages. When you have a direct interface to the operating system, you need to understand the operating system probably well, better than, let's say, some other things. So the abstraction mechanism that we discussed earlier, we said we need an abstraction mechanism, right? So that means that here, perhaps that abstraction has some holes in it, or maybe a different understanding of an abstraction here. So they say blazingly fast compile times. This is like a, I don't know, like a salesman would actually do, not a computer scientist or a computer engineer. Memory safe subset. This is interesting. There is something apparently called memory safe, a subset. What is, I don't know what this subset is. We need to understand it. We need to probably read it. It says maintainable and easy to understand code. So this is good. So you see that there are two things here. When you have a code, you need to talk about maintainability. What do you mean by maintainability? Yeah, someone writes a code, or I wrote a code, let's say 5 days ago. Now I need to actually, let's say, continue using that code. Maybe if it doesn't change, if it doesn't need anything, so it is already maintained well enough. But if I need to actually add something to it, or if I actually, that code needs something more than actually it actually does, or maybe something has changed in my requirements and I need to actually update it or add to it or change it, that maintainability is actually becomes very important. So you have seen this from time to time. When you actually try to write someone else's code or maintain someone else's code, you usually can get very quickly frustrated, and you would tend to actually rewrite it by yourself, because your rewriting should, you think that your rewriting would be more maintainable than other person's rewriting. So this has, of course, a lot to do with the style of programming that people actually do. So it's not just the language's ability to actually make something maintainable, but sometimes language can actually have useful concepts, tools in them that would actually make this maintainability easier. And we are going to see these type of examples later on. And easy to understand code. So maintainability has something to do with readability, and also readability from not just being able to read what is written, but also understand what it is trying to do. So this type of easy to understand code seems to be good. Okay, so gradual learning curve. They are saying that they are using C-like syntax similar to Java and others. And then if you know C, you can actually learn, and you can gradually add new learning, new capabilities of your programming. This is kind of similar with Python as well. Python will probably say many of these things like gradual learning curve, maintainability, easy to understand, probably not so blazingly fast compile times, and not necessarily direct interface to the API, and not necessarily high performance computing, but let's see what happens later on. Compatible with C++ application binary interface. This is interesting. Now, what this is saying is that if you are able to actually able to kind of interface or able to use, or let's say you are compatible with C application binary interface, you can use a lot of things from C, and perhaps you can use also this thing for from C as well. So this type of compatibility could be important, but then it will probably bring a lot of complexity to the language. And from that perspective, I'm not 100% sure now that it is, let's say, as maintainable and as easy to understand as they claim up there. And then you can, they talk about limited compatibility with C++ application binary interface. They are saying that they are using multiple paradigms. So what are those? Imperative, structured, object-oriented, generic, functional programming, purity, and even assembly. So they put everything in there. This is similar to Python. Python tries to put everything in there, perhaps not assembly, but now the question is, why do I need assembly in a language that actually also has object-oriented and functional programming purity in them? So these are probably conflicting things. If I'm talking about functional programming, most probably assembly doesn't fit in there. Assembly is imperative as a kind of as a basic language, right? So all of these built in together or put together, you put into the same, let's say, bucket together, probably it will have some problems in it. So they are saying also this is good. They are saying that they have built-in error detection. So these contracts and unit tests, these contracts and unit tests they are kind of new ideas in programming, new not paradigms, but these are new concepts that actually are useful in, let's say, building large systems. So when you have, if you have, you can have, let's say, a built-in support for these type of things as a language, as far as the language is concerned. So these seems to have these. I don't know how, in what detail. Or you may have, let's say, libraries around this, some sort of, let's say, user-defined or let's say later developed libraries that might provide some of these capabilities. So this is all these things, when you actually put together, we are going to see later on that you have potentially a non-orthogonal system, meaning you have overlapping stuff that actually you have things that you can do, you can use instead of each other for in many places. So we are going to see that non-orthogonality of a language is not a good thing, because if I am able to do one thing with many in many different ways, in 5, 10 different ways, then I need to learn all of these ways, and that learning would actually become complex. And when two things are used to do the same thing, most probably they may have some, they may not be exactly the same thing. They may have some differences, and that differences might require you to learn, let's say, minute details about those things, so that that learnability could be suffering from this. And they said that they have an easy to understand code, and they said you can do gradual learning. You have a gradual learning curve. So This means that you will learn stuff and learn and learn and learn and learn. Ideally, a learning curve should be, let's say, should start slow and then perhaps go very fast, let's say, right? So, or another possibility could be actually a linear curve where you put 10 effort, you learn 10 things. You put 100 effort, you learn 100 things. And then probably you will not learn everything because you're not going to put so much effort. So this type of a learning curve is probably not so good. So depends on, again, application and the people that is actually using this thing. So you see that actually some of these things are kind of C-like or C Java-like. Some of these things are kind of you see an example here on the right. So you have this import thing, you have these semicolons, and then all these curly braces, this type of type declaration statements and functions, and perhaps some other things like strings and so forth. Right. So this is one specific language that that claims these things. So we understand some of them, but when we after we finish this course, when we come back to this thing, we are going to say, okay, you know, I know what means what do they mean, what they mean by this memory safe subset. I know what what it means to have, let's say, an imperative and functional programming purity all together in a single language, right? They have again, you can read this through. They are saying that this language enable writing fast, effective code in a straightforward manner, make it easier to write code that is portable from compiler to compiler, and so forth. Now, I think this is a rather, let me see when it came up. I forgot when this thing was around. So let me see. Where's my cursor? Interesting. My cursor is gone. Okay. So the question is, if this is so good, why is it actually not in our list of languages, that 52 languages that we have? Or maybe it is in the 52, but we haven't seen this in the top 10, right? So it should have been on top 10 if these are all good things to actually do, right? So again, there could be a lot of reasons why this language is not in that top 10 list, but most probably the choices that they make here, is appealing to a smaller, let's say, problem domains. So a domain of, let's say, problems that could be solved using this thing, maybe it's a smaller set of problems. Maybe a smaller set of people need such, let's say, high-level constructs, high-performance static typing, and so forth. This could be one reason, or some of these reasons could be these. But it could be also that maybe they didn't come at the right time. Maybe Python was already there, and Python was missing maybe this high-performance stuff. But who cares, because you have so much power in the computing hardware, you don't worry about it. When C++ was kind of used in the enterprise community quite a bit, or at least in the beginning, we had these Microsoft Foundation classes. So Microsoft has these C++ tools. You could call them earlier version of this .NET stuff, right? So it was around, and we in our lab we had a reasonably powerful and new set of just newly bought desktop PC, and this was running Visual Studio, whatever at the time, maybe 4 or 5, I don't know, I don't recall exactly. So just a simple Hello World application, the compilation of a Hello World application was taking like 15 minutes using this MFC, this Microsoft Foundation classes stuff. It was not a bad machine. And this was 94, 95. And it was taking a lot of time just to, I mean, this code here, the code that you see on the right here, of course, this is not as simple as this one, but with a window that you want to actually put a few buttons and so forth, was taking kind of 15 minutes to compile. Now that 15 minutes is maybe 15, I don't know, maybe not necessarily nanoseconds, but maybe not even milliseconds, but not necessarily, maybe let's say a few seconds. So what made that difference is from then and now is computation power actually, as you know, kind of doubles every 2 years or so. So what is done, let's say in 15 minutes 2 years ago, without doing anything, any improvement on the thing, you have you can actually have it by now. So every 2 years, it actually goes down by half in terms of let's say speed, maybe memory and so forth. But anyway, so now when you have such a thing, why do I care about high performance stuff? Why do I care actually these type of things? Maybe it is it's much easier or much better. It's much better to have something more readable by everybody, right? Data scientists, if a data scientist, a biologist, let's say a statistician, or let's say business administrator or whatever, if they can use quickly program your language in your language and actually build something quickly out of it, and even if it runs slow, who cares? Right, and then 2 years later, that slow is not going to mean much. So probably because one reason behind this is that there are some other languages that actually have a better, or let's say the same set of features, subset of features, but with the right choice, giving up on, let's say, high performance, they might have actually made it much, let's say, much more appealing to a larger community. Especially interpreted languages have that appeal, because you type something, you see something. You type another thing, you see another thing, right? So why do I care about actually if it is, let's say, not giving me the answer right away in milliseconds? Okay, I can wait a second or so, but if I can get it and I can see that I'm making a mistake or it is working, then I move on my second and third and fourth steps. Then that might be actually a good answer for me, that I look, or I actually look in a language. I try to see that my language should actually give me this immediate feedbacks. And on top of it, if it actually has other possibilities, other capabilities, then it might actually help me better and better, and that language then can have a better footprint in the community. So it's not necessarily all these things, let's say one of these things made or didn't make this language popular. It's probably a combination of things with the design choices and what is happening outside in the community that actually made that difference. All right. So you can read this through. So for example, it says they are doing functional programming. They are using functional programming paradigm in this language. They say that it has a lot to offer in terms of encapsulation, concurrency, concurrent programming. This is being able to run your program on, let's say, on multiple resources at the same time. Like if you have instead of one CPU, one machine with one single CPU, what if you have, let's say, multiple CPUs on that same machine, or maybe you have multiple PCs with multiple CPUs. So is your program or your programming language, can it actually support you with within in such a case? If it does, then it is good. If it doesn't, then it's not necessarily so good. So if you are doing, let's say, simple app development, maybe this is not a big deal for you. But if you are doing, let's say, an app development that requires very strong, let's say, or a very efficiency, like you are doing image processing, for example, or sound processing, or you are trying to, let's say, write a, let's say, an algorithm for your banking application to do, let's say, a face-based authentication of your user. So you wouldn't wait 5 minutes to actually get authenticated. You want to actually get the authentication done very, very fast. And if you need to use, let's say, the multiple cores on the machine that you have, then you need concurrent programming. Now, concurrent programming can be done with, even with, let's say, assembly programming, if you have the stomach for it, if you have the, let's say, the mind, the brain for it. You can do this with C, you can do this with C++, but, and you can do this with Python or some other languages like even Lisp, right? The question is, when you do this with, let's say, with Lisp or with D or with C++ or with Java, what type of concepts, useful concepts, do those bring to you? Do I need to use a library, or do I have native support? And even if I'm using a library, how easy it is to actually code that library? So if I need to actually know every little detail about these things, then it might be very expensive to do it. I need to learn, I need to try, I need to, not just the learning. I may think that, oh, you know, if I give you these things to you, you'll do this like, I know these things, I'm done, I can do it. But usually when you try it first, it doesn't work. And even if it works on your machine, it doesn't work on, let's say, on my machine. Even if it works on my machine, 2 days later, we find a bug in it that actually breaks up everything, right? So why does this happen? Because it depends on actually your experience. So your experience with the language might have a lot to do with how safe, how correct your, let's say, program or your algorithm is going to be. And if your language somehow makes that, let's say, helps you with that without learning, without being so careful, without going into the gritty details of everything, and if the language actually provides you support for that, then perfect. And functional programming actually does this through encapsulation and some ideas, memory safety and composition and so forth, right? So they are saying that this thing has pure function. We don't know what a pure function is. We are going to learn about this one. They talk about immutable types and data structures. And then they talk about lambda functions and closures. We are going to learn about lambda functions and closures. You might have learned about them or used them in the past, but these are useful concepts, especially functions and closures. Lambda functions and closures are useful concepts that comes from math that may make your programming, let's say, or programming quite easy, because you are borrowing things from a discipline that has proven itself to be doing it right and bringing it into this discipline, and it may actually be very, very useful, and we are going to see examples of this. There are a lot of other things like automated memory management. They have this RA two type of software development technique to manage resources and deallocation. So these are things like, if I can say it very easily, if you have a, let's say, a class-based object-oriented, let's say, concept here, in a this would actually not, let's say, the initialization or construction of an object may require certain, let's say, initializations regarding memory and so forth. So this is a concept that actually kind of orders those things. C++, 11th edition of C++ has, for example, this particular concept. So they are saying that they have this one. We are going to see a lot about this memory management, automated or explicit. What is explicit memory management? For example, they say, I mean, if you have a, for example, a garbage collected language, your memory management is automated and implicit. But sometimes you know that garbage collection is a good idea, but an expensive idea in terms of actually the algorithms running in the background to do this garbage collection may not be what you need. So it may be too costly for you to do the garbage collection in an inopportune let's say, timing that you don't want it to happen there. So in those type of cases, they are saying that, okay, we actually add an explicit memory management where you can override what an automated memory management thing is going to be doing. For example, this will be most probably with the allocators and let's say constructors and destructors, right? So in those cases, they are saying that you can actually override, for example, the perhaps the default mechanism and then put a new mechanism that might favor. These are very, this is a nice idea, but it's a very, it's a difficult idea that you need to understand and you need to actually know about these things, and you need to understand a lot about let's say, the underlying things happening in the language so that you can actually override things to do it better. So this would actually kind of remove that abstraction idea or hinder that abstraction idea a little bit. Okay, so I don't want to go through the entire thing. For example, they are saying that even with the project management, they are helping with the language itself has certain built-in things, built-in support for generation of multiple versions of a program. So this is nice, but can someone tell me what will be the downside of such a thing? Again, this language is saying that they have built-in support for generation of multiple versions. So the idea is if I am actually having two versions of a program in the same source code, right? I can, let's say, in C, I can use, let's say, sharp if and end if blocks. I can say, okay, if this is a Linux version, do this and this and this. If this is a Windows version, do this and this and this. If it is an iOS version, do this and this and this and this, right? So this is the C preprocessor way of doing things. And these saying that we have built-in support for generation of multiple versions. So that means that probably they have some other commands, not these preprocessor commands, that actually helps you with doing this. So what is the downside of such a thing? Can someone comment on this? Anybody? Are we all sleeping?
Can I say something?
Sure, you can say.
So I think the downside may be because we would have to write different code for different operating system for different generations. So that may be that may add another layer of complexity to the language.
So instead of having this in the, let's say, in a preprocessor like in C, these people are saying that, okay, I have, let's say, 3 or more commands or more, let's say, functions or whatever that is, that construct is, right? that I can use those to actually do the versioning. So, all right, so replace the C preprocessor by with a command. Now, as you are pointing out, that this means that I need to know what those commands are. And I need to, let's say, I mean, that would add on top of the complexity of the language in terms of learning. All right, fine. If I don't want to use it, I don't use it. So this kind of fits into their description of gradual learning, right? So if I don't use it, I don't just even learn it. I just use whatever is convenient for me or useful for me. Now, this type of things, of course, could be nice, but the cost is, let's say, complexity, which you can manage it by saying that, okay, gradually make it complex, don't use it, but still you have this language that actually is capable of doing these things, and you are using only a portion of it. Now, if I'm using only a portion of it, why am I using that language? Maybe there is another language that actually does it better, I mean, does it the same way, and perhaps with a simpler, let's say, instruction set, or simpler, let's say, syntax or semantics, right? Now, from the user's perspective, when you have things that is complex, you might actually question it, or you might even get discouraged because of that complexity may kind of scare you, right? So gradual or not, it doesn't matter, right? So most probably the other thing is that there is another way of doing these things, right? So usually when you do this type of project management, version management, you try to do this in a higher level, kind of outside the code, outside the language. Why? Because when you do this outside the language, you do it when you need it, and that will actually help also with this orthogonality stuff, that if you have a way of doing this outside, bringing it inside may not necessarily be such a good idea unless it actually improves something else quite a bit. And here it doesn't seem to be improving something else. Therefore, it may not be such a good idea. Of course, we need to actually see who uses these things and in what way this is being used. So let me see. Sorry, that's fine. Now, this is again, this example, I gave you this example just to see what, when you encounter a new language, what type of, let's say, language you would be actually kind of encountering. So what are they going to tell you? They are going to tell you a lot of these things. And you are going to say, okay, now, do I understand them all? Some of them I do understand, and some I don't understand, perhaps right now, as I mean this class, right? So at the end of the thing, hopefully you'll have more understanding than what we started with. So that being said, we have a quick look at the schedule of this course. We'll be having our midterm somewhere between 8th and 9th, after the 8th week, the week 8. So we'll be looking for lexical and syntax analysis for 2 weeks or 3 weeks maybe. And then we are going to talk about names, bindings, and scopes, and then typing systems, and then expressions and assignments, and then control and subprograms. These are mostly generic things, but we are going to be covering them in the context of imperative programming paradigm. Then we'll talk about functional programming, and then we'll talk about a little bit of encapsulation, and that will lead us to object-oriented paradigm, the differences between several languages that use this object-oriented paradigm. And then we'll be looking a little bit into also exception handling and the concurrency, because I mean exception handling and concurrency goes in together, because concurrency or exception handling, they are both related to actually let's say the flow, the control flow will be changing or will be split into, let's say, into different potential branches, and you need a mechanism. Most languages will require a mechanism or will implement a mechanism to handle those. And then we'll conclude with logic programming, and we'll talk about Prolog in that context. So let's take a 10-minute break. We'll resume at, or 8-minute break. We'll resume at 10 after 3, and we'll continue with the next part of the this week's class, where we'll be looking into paradigms and metrics or some sort of evaluation criteria to actually say that one language might be a little bit better than the other because of what. So we are going to discuss of those whats. So I'll see you in 10 minutes or 8 minutes. Okay, let's see. So I actually wrote a short note on the chat area. There will be a PS session on Wednesday at the regular class hours. So there was a question in the beginning about the PS session, and the homework is going to be, I think, announced later today. So if you are, the PS session will cover a little bit of Lisp. So if you are very new to Lisp, you may want to attend the PS session. Okay, so what we are going to do now is go back to, again, to our schedule, and I'll be talking a little bit about evaluating programming languages, how we do it, and then I'll define some of the major programming paradigms, and then this is kind of you know these type of things, but I need to go over, redo this thing, or go over a little bit about the compilation process. And when we talk about compilation process, we'll probably discuss a little bit the basic architectural model that we are using, namely von Neumann model, and we are going to talk about how it is related to all the things that we are discussing here. So when we actually look at a language and evaluate it, we can mainly ask the questions along these lines. We can ask, how readable is this language? How writable is it? Is it simple? How simple is it? And simplicity goes with this orthogonality. How many features does this thing have, this language have, that is actually unique? Are there, let's say, overlaps between the features? Can you do things, the same thing with many of the features of your language? The other questions, what is the expressive power? Does it actually, when you say one thing, and it actually does a lot? And does it offer flexibility? So you can see that already this simplicity and expressiveness and flexibility kind of starts challenging each other. Is the language reliable? What is the reliability? How does it handle reliability? When I write a program, how vulnerable is that program to, let's say, programming errors? Can you actually, at what level can you check potential errors in your programming? Of course, this is the safety is kind of the question that we ask here. And then the other things around cost. Yes, the cost is influenced by all the above things, but in terms of cost, in terms of creation, how much time, how much money, how much effort does it take for me to create a program, execute, or let's say create a program, meaning program it, write it? How much time, effort, money do I actually spend on execution? Does it go fast? I have the same type of a thing. Let's say I have a problem, very simple problem. I can solve this problem at the same, so the program, writing the program takes the same amount of, let's say, effort and time and so forth for two languages. Does it take the same amount of time to execute the program at the end, right? If one taking twice as long, always time is money, right? So the time is money, so that will cost you. And also one of the important thing is, again, cost in terms of maintenance. How maintainable is this code? I can write probably very fast code, not necessarily always the case, but maybe it is very difficult to maintain. Or maybe I can write, let's say, a knowledgeable person like C, for example, may write very neat, compact codes, but let's say an average programmer may not be able to actually maintain those codes. So this is influenced by the readability, writability, and so forth. But these questions that we need to ask to evaluate a certain any programming language that we might have. So, what is readability? The question is coding easy and fast to read and understand? So, let's say I asked, I don't know, let me pick someone from this list here. Apparently we have a lot of people, 154 people attending. Let's say Berke Belgin. So Berke, I'm asking him to write a specific program, and then he gives it to me and says, okay, here it is. Now I'm looking at it. Now this is gonna be important. Am I able to read this code and understand it by just looking at it? Do I need to split? I mean, do I need to spend a lot of time and energy to understand it? So if the readability is, this is very important, probably very, maybe one of the most important things, right? So this is, this actually readability kind of, if the readability of a code, reading and understanding of a programming language is important, which is, then the first thing that you would probably look for is overall simplicity. So if the language is simple, reading will be easy as well, because I don't need to know too many things. I need to know only a few things. So the lesser the number of features, the better, right? So too many features is gonna be bad for readability. And multiplicity of features is also bad. Meaning, if I am actually doing the same thing with 3, 4, 5 different instructions, then this will be bad as well, because I need to know them all, because Berke might use one of those, let's say, things, and let's say, who else is here? I don't know. I'm gonna ask Berke later on a question probably. So maybe Elif Akgün, maybe she's also using another, let's say, feature or another instruction set. And I'm reading the same thing. I'm the same reader, but the same thing is done with in two different ways. I need to actually know both of them to be able to read. Because I cannot say, okay, hey, Berke is never gonna use the second feature. So let's ask the same thing from, let's say, Elif Akgün to actually do the same thing, and don't never use that. No, that you cannot guarantee that. All right. So here also comes the orthogonality. So multiple features, if the multiple features is bad, orthogonality says that I would actually have my feature set of features. They don't overlap. They are necessary. If I take one of them away, I will actually lose something in my language, lose an ability, right? So if your features, when you take some of them away and you are still able to do the same thing, then your set of features for your language does not support orthogonality or does not do good in orthogonality. So this makes the language easy to learn and read, and also meaning in this case will be context independent. Because if I am doing two things, I can do the same thing in two different ways. Most probably, I have a context associated with one of them to choose one, or another context for choosing the other one, right? So if I have this context, different contexts defines different feature sets, then this will be difficult to actually learn. So it should be that my language features should be context independent. I shouldn't know about the context, meaning the problem that I am solving. I don't want to look into, let's say, I don't want to know about, let's say, right now, if I'm looking at a right line command or a function, I don't want to know about, let's say, 10 what happened, what was the context 10 lines above or 20 lines above, right? Control statements are important. Do I have built-in control statements? And then data types and structures. So what type of built-in data types and structures I have. So for example, you'll see that, let's say, if you look at C has, let's say, 3 different ways to actually do loops, right? This is not so in some other languages. For example, Python might have only 2, right? So you use them for different things, but you still need to learn them. And most of you have taken C from me. So when I talk to you about let's say loops, we actually talked about a concept where you have a kind of an initialization, you have a body that changes what happened in that initialization, and then you have later on kind of a check that if your whatever you have done has actually satisfied your condition to stay in the loop or continue doing the same thing, or if it is actually telling you actually to get out. So the question was always, why do I need three features? C had it because each of those had minute differences in terms of usage, but they could have actually saved you from 1 line or 2 lines of extra lines of code, right? So C, again, if you recall, had the kind of the idea behind C was they wanted to have very efficient language in terms of the code that is generated, right? So then kind of avoiding 1 or 2 lines of code could be very, very important, right? But if you are not as concerned about having 2 or 3 instructions to be added to your, let's say, to your control structure, then why do you care? So then just do it 2 things. So for example, Python has of loops. One is kind of a counting loop, not even a counting loop. Python has kind of an iterator, iterates over a set of values. And this could be, if the set is, let's say, a set of consecutive numbers, then it will be an let's say a counting loop. Or it will have a while loop where it will actually just do certain things and check. So in this case, for loop for, let's say, C and Python has different meanings, and while has something else. So now for and while has some overlap, but I don't put a do while on top of it to actually make that overlap even bigger, right? So these type of things, what you have in that control statements, built-in control statements, and what type of data types and structures you have. So if your data types and structures are very, very involved, then you need to learn them all. But we know that some of these things we avoid by actually having, let's say, very limited number of built-in data types and structures, and then use user-defined types and structures to actually expand upon it, right? And then finally, syntax considerations, closeness to natural language, and or maybe something else like mathematics that we know of. So if my syntax is close to math, which I have been learning since, I don't know, grade school, could be very, very easy for me to learn because I am used to it. I am familiar with it. I don't need to actually know the new concepts, right? So you might have asked that question maybe when you first encounter, let's say, an assignment statement in an imperative language. I certainly did. So learning, let's say, math in arithmetic in as early as probably the 4th grade and 5th grade, and more in the, let's say, middle school and even more in high school. When I encountered with programming in C, and there was a statement like I equals I plus 1, right? Now this is an assignment statement. We know this assignment statement, and the syntax seems to be suggesting a mathematical expression, right? Or a formula or an equation. And we always know that I cannot be equal to I plus 1 in semantics, at least, maybe, not necessarily in syntax. So, but in that case, at least on the right-hand side of that equality, I know what I plus 1 means. I don't need to worry about learning about it. Perhaps the I equals part is kind of strange, and that is a deviation from what I know in, let's say, in algebra. Then I need to, let's say, learn that. So this type of familiarity, closeness to either natural languages or to mathematics or something else would be actually desirable from the syntax consideration, and it will make the language more readable. Writability is also important. The question is ease or speed to create programs, right? To solve a problem that I'm actually trying to do in a specific problem domain, right? So same thing goes here. If I have simplicity and orthogonality, then I may be actually able to write simpler programs or easier. My writing would be easier. So more features would mean that I need to do more. I need to do more lookup. I need to do, let's say, read or understand every feature very well so that I know where it actually, in what problem it is best to use, let's say, do while versus while versus for, right? So if I had only one of those things, let's say if I had only 4 loops instead of, let's say, while and others, then I know that I need to actually formulate my problem to just fit whatever the for loop is actually allowing me to do, right? Perhaps that's not such a good thing just to have one of those constructs for the loops, but that makes it simpler to use. It doesn't mean that it is, let's say, flexible, or it is gonna, let's say, help me solve problems much easier, because if I need to convert every loop to a counting loop, then I'll do something more in terms of converting an algorithm, or let's say building an algorithm, and maybe converting that algorithm to that specific language, right? Support for abstraction is also important, right? So if things are quite abstracted, I don't need to know about details. I say, okay, for example, let's say typing, right? Integer. I say just integer. It's easy. I know it. And if I have, let's say, a type that, let's say, if a language gives me a type that has nothing to do, I don't need to know anything about, let's say, the limits of that number. It is infinite precision. So if I need to actually use a number to do any numeric operation or number operation, then I just use it. I don't need to worry about the limits. Do I use 16-bit integer here, 20-bit, let's say 32-bit integer there, or 64-bit integer there, or maybe a new type that is actually not even existing there. So, but again, that is good. So that abstraction, if I had that integer type that just does integers from minus infinity to plus infinity, perfect. But is there any language that can support it? Perhaps so, but very, very difficult, right? So some other gives to actually take that, let's say, abstraction. So, but abstractions are good for writability. Not many of them, of course. Simple abstractions, support for abstraction would be very, very important. Now, perhaps in kind of conflict with simplicity and orthogonality, expressivity is important, right? So you want your let's say instructions. Let's say if you are doing imperative programming, you want your instructions to be very expressive. You say do it, and it does it. Of course, there is no do it command, right? So if you want to say do it command, you have to actually break it down to things that are doable. So the more expressive the language is, right, the better. But then it would most probably put some pressure on simplicity to support that expressivity. And then the other thing, this is a little bit peripheral thing. So development environments. Do I have any development environments? What type of development environments does it support? Is it let's say maybe it's a compiled versus interpreted, and usually, let's say, writability in interpreted languages might be a little bit easier than compiled ones, because you get, let's say, instant feedback on what's going on, and especially your errors that can actually be visible to you very quickly. Whereas in a compiled one, and if you, as I said in the first hour, if your compiler takes 15 minutes to compile a Hello World application, then, or maybe in the older times, like in the 60s and 70s, when you have these punch cards and you punch a thing and you give it there, and then 2 days later they say, okay, let's say a simple error, let's say undefined function somewhere, then you are done. You have to go back and actually do the same thing. So this type of compile the environment is quite important. Of course, nobody does punch cards anymore. Nobody waits for 15 minutes to compile the thing, but still there are things that actually takes a lot of time. For example, we do, let's say, artificial intelligence stuff, deep learning stuff. We feed our data, and then sometimes the training takes like days and weeks and maybe months. And you don't want to get, let's say, things, let's say, into second month of the operation, you get an error that actually doesn't do, let's say, it's just a simple syntax error or whatever, right? So that's important. So simplicity usually improves writability and readability. Readability and writability, because a large language makes more time to learn, takes more time to learn, right? Programmers might learn only a subset. This is certainly the case with some of the languages that we know, like Python, and the one that we discussed in the last hour, right? So you might only learn a subset, and that might be enough for you to actually do certain things, right? Feature multiplicity is often confusing. You don't want to have features should not be features should not be in multiples. So, for example, if you are doing decrementing a variable in 4 different ways, then you have a problem. Why would you actually do incrementing or decrementing a variable in 4 different ways? This one. We have it in C, right? We have, or C++, maybe 3 or 4 times, right? So 4 different ways. Right? Operator overloading, for example, right? So these are sometimes good concepts in terms of, like, let's say, abstraction, maybe, and also some other things. But when you overload an operator, you need to know how many overloaded things actually are there. So you need to actually know about those things. Okay. Some languages can be too simple, right? So too low level. So in those cases, what you would need actually is you will need too many, let's say, instructions to do things that you might have done in other cases, let's say with a single instruction or a few instructions. Right. So this type of answer, I mean, this is supposed to be an important thing. So you cannot just say, okay, I want to have a language that is, let's say, just have 10 features. No, it might be too simple and it may not be useful. It may not be useful at all. If this was the case, then we would have stuck with, stick with assembly language, right? We didn't do it because those are not expressive. You need expressiveness. You need concepts, abstractions that will help me achieve higher level things very quickly. So when those type of things kind of added to your feature set, then your language will become complex. So there will be always a balance. How complex you want to go? So sometimes you may say, okay, heck with the programmers. They are very smart people, and they can study hard, and they can learn any language that I can give them. All right. So this might be your thing, and then you can add, let's say, zillions of features into your language. This is not a right approach, of course. Nobody is limitless, and you might be, okay, one of you might be very, I mean, it might be very easy for one of you to learn such a language, but maybe for another of you, it may not be so. So this is, in that case, it's a kind of a balance that, yes, you want to actually have simple so that we can learn, but expressive enough so that we just don't do, let's say, simple stuff and play around with it. We do real stuff with it, right? Orthogonality is again having orthogonal languages actually has features that are built upon a small mutually independent set of primitive operations. So this is usually fewer. This means that actually you don't have exceptions or fewer exception rules that would actually go to conceptual simplicity, like restricting types of an argument to a function. If you restrict a type of an types of an argument to a function, then you would actually will have simpler things. But again, you would probably lose a little bit on the, or maybe a lot on the expressiveness side. And here also trade-offs with efficiency. This trades off with efficiency, because again, if I have conceptual simplicity, when you have, let's say, complex concepts, you need to actually build a lot of things to achieve that complex concept. So the efficiency of programming might be actually a problem, right? So also the resulting program might also be not so efficient. So this is another part of it. I mean, there are examples that here having fewer constructs and having few exceptions increases readability and writability. This is orthogonality means better reading and readability and writability. They are easier to learn, these orthogonal languages. For example, pointers should be able to point to any type of a variable or data structures. This is in C, for example, you have exceptions are due to lack of orthogonality. So you actually put, again, exceptions in C. So you have here an example that you have a different add operation depending on the operand location in memory. For example, here you have 3 add. And again, these are, okay, operation wise is the same, but the difference is actually the kind of the operands, if they are in location, depending on where the operand is in memory, you have 3 different instructions, and this is assembly language. So these are the exceptions that you have. So exceptions in terms of operand location, and you have difference. Now, of course, efficiency perspective, when you have an add R and add RM, these are probably implemented in the background with these exceptions in mind. So they would actually do very well if you use actually the, let's say, register and memory to register, right? So if you are adding a register and a memory to a register and storing the result in a register, then you better use add RM, because that will be optimized for that purpose. If you can perhaps use actually add operate, let's say register to register 1, you can do that. But then what you would do is you would actually do a move operation from one of the memory locations to the register, and then add those registers to and store them in the register. So from the efficiency perspective, you have probably an extra instruction in between that will actually that will cost you. So add will require a move operator or move instruction, whereas add RM will not require such an operator, right? So that would actually probably much more efficient, twice as efficient probably in implementation. Now, usually two of anything is usually bad. So if you have a 2 orthogonal, let's say, language, an inexperienced programmer might assume that they can do something that makes no sense. For example, if you have, you can add add 2 pointers together, right? So if you had only one operator add, then the inexperienced, what you need to do then in that case, you need to understand that. So the add has all these context, and you have to actually make sure that those contexts actually are handled properly, like adding 2 pointers together. So we talk about support for abstraction, especially for imperative and other languages as well. Data having kind of looking at the programming as a data and a procedure, where data actually is programmer-defined types and classes. This could be also in object-oriented languages as well. And class libraries, whereas procedural is looking at this as programmer-defined functions and standard function libraries. And now the data, how you actually say abstract these concepts in this language is different. So in one case, data is actually again defined as programmer-defined types and true programmer-defined types and classes and class libraries in one form of in one paradigm, and in the other one, in the procedural paradigm, programmer-defined functions and just standard function libraries. Okay, when we come to reliability, program behavior is supposed to be the same from on different platforms, right? So reliability means that I think I said it wrong in the beginning. I said reliability. I confused reliability with safety when we started this thing half an hour ago. So reliability is that your program, let's say you have a C program and you run the C program on different platforms, it gives you the same results. So the language needs to guarantee that, right? This means that this means other things like types are detected. So the semantic of what is intended with your program should be actually clear. When I say, okay, this means this, when I say, okay, these two numbers are going to be added and I'm going to get something out of it and it's going to fit in the memory, this is supposed to be controlled by, or if the language gives me a guarantee that using that plus concept, let's say addition concept, I'm not going to have any trouble unless I actually give a wrong thing, then that language will be reliable. Semantic errors are properly trapped. So we need to actually, if the language is able to support some semantic errors, and they can, or semantic error checks, like things like memory leaks and so forth, it should be able to actually prevent memory leaks. This will be helping reliability. We have an example here. This is, so when we look at this guy, this is kind of the semantics. This might, such an expression or a statement may mean several different things. Here I have 3 different things. So the question is, if this is not clear by when I type it, I need to know as from this concept-wise, this is supposed to be one of these things, not 3 of them, because those 3 would mean different outcomes. So it should actually give me the same outcome. So this is the semantic side of the thing has to be clear, or it is as clear as possible, or as unambiguous as possible. So there is an ambiguity here, and I can read it one way and you can read it another way, and the compiler reads another way. Then we are in big trouble, because that program is not going to do what we assumed or what we supposed it would do. Efficient implementation is another thing, important thing, especially for embedded systems. So real-time responsiveness is required. If I have an embedded system controlling a robot, then when I say when I know that the robot must act in a certain way, I should be able to actually get to that certain get that command to the robot in time. I cannot wait. Web applications, responsiveness to the users, so is important. Even if you can think that, okay, you know, in a web application I don't need as much performance, you will think wrong, because you would probably need more performance in a web application as well, or quite a bit of performance, because if I'm typing a search and then it's taking minutes to get me, I will dump Google and I will go for somewhere else, right? So like things like, let's say, a corporate database application, if I am doing a search or an updating in my database, it should be done quickly. So my language should let me actually do this quickly. I cannot wait forever. Okay. So when we look at actually the characteristics in terms of what type of characteristics a language might have, from simplicity to orthogonality, data types, syntax design, support for abstraction, expressivity, type checking, exception handling, restricted aliasing, and so forth. These are kind of features or some sort of conceptual, we call them characteristics, versus the criterias, those readability, writability, and reliability criteria. You see that actually simplicity is playing a role in all of them. Orthogonality as well, data types as well, syntax design as well. support for abstraction, not necessarily in reliability, but the other ones, expressivity as well. Type checking is all for reliability, exception handling and restricted aliasing. Exception handling might, I mean, as a characteristic, it may add some readability issues and writability issues, but when you have one or when you don't have one, reliability is going to suffer. From the okay, I think I am 2 minutes over time. So from the cost perspective, you need to think about programmer training, the software creation, compilation time, and the resources required for compilation. So you might have a very good compiler, right? And it may give you very good program at the end that actually runs blazingly fast, but the compilation, they say, and it's reliable and so forth, right? Because it does all those checks that you want to do. That is, we are going to talk about that if it is possible to do such a thing, but anyway, but it takes days and days to actually compile, and it requires parallel computers and it costs so much money. So that doesn't make any sense, right? So compilation should be important from required resources, including time. Compiler cost, you might have a compiler that is actually very, very expensive or cheap or free or whatever. Reliability, if your language is not reliable, then cost is going to be a big issue. Maintenance is very, very important in terms of cost, because nobody actually writes a program and just gives it away and then they are done. They get their money and they can retire in an island and that's it. No, that's not the case. When you actually in real life, when you have a program that when you solve someone's problem with programming, the solving part is probably the easier part if you have a solution in mind. Of course, finding the solution might be actually quite difficult, but what we usually know is that maintenance takes kind of so if you actually divide the cost of an entire solution to a problem, finding the solution, implementing it, and actually deploying it takes probably 1 unit of time. And making sure that that deployment works reasonably well, which we call productization, that takes another unit of time. And then maintaining it, just to make sure that it works as intended and you handle your customers or users, let's say, problems and so forth, it takes another unit of time. So this is the least. Usually that maintenance is actually more expensive than that. So if you have a language that actually supports you with this maintenance, then you can actually go down in that required time and energy and money, of course, then that would be actually good for you, because that's where one of the major cost comes from. There are other things like well-definedness. This is mathematical generality applying it to other problems, and I mean to everywhere, and portability, being able to actually use that language anywhere or compile it anywhere is important. We are going to talk about this, but these are not as important as the ones that we discussed. So that concludes today's lecture. We'll do a PS session on Wednesday. So there will be attendance taken. So we'll take attendance on that as well. So it's a must attend event. And I will stop recording now and I'll ask